All right, so today we start our last topic, parallel algorithms, a bit more rushed than I had intended because of my failing to notice the change in the Thanksgiving calendar. This is a topic that, from a theoretical computer science perspective, really flourished in the 1980s when people started studying these parallel algorithms and developing a rich theory for them. And then kind of died away in the 90s because the parallel models they didn't match very well with what people were actually seeing in practice on computers. I think they're kind of coming back now because as we move to multi-core, you kind of are forced to think about parallelism in a way that you could avoid in the 90s. The models are still very simplistic, but even so, they give some great insight about the ways to design your algorithms for these systems. And they're also, of course, very interesting from a theoretical perspective. So in talking about parallel algorithms, I'm actually going to very quickly show you two really quite different models of parallel computation that end up being pretty much the same from a theory perspective, even though they're very different in practice. One model is circuits of logic gates. And the other model is parallel processors, all executing at the same time over a shared memory. And in both of these models, we're going to be asking how one develops good algorithms or good circuits. But what does good mean? Like, what is a measure of quality of a particular algorithm for solving a problem in parallel, or of a particular circuit for computing the value of some function? Anybody want to propose for either model how you might measure the resources that we want to optimize?
High parallelism.
So what does high parallelism mean?
Given an infinite number of processors versus some finite number of processors, and the speed up.
Okay, so speed up relative to a sequential algorithm. Yes?
Yep.
Good. So if I'm going to be talking about speed up, it makes sense for me to be talking about speed, right? The number of steps that it takes to solve a problem, right? Just the time, basically. But there's another important metric that you've already alluded to, right? Besides just the speed that you can achieve.
Like the amount of scales for the number of processors?
Yeah, well, so exactly, the number of processors, right? So we'll see actually a few examples of problems that it's possible to solve incredibly quickly if you use an insane number of processors, but where they take more time if you use a plausible number of processors. Okay. Okay, so that's pretty natural, but let's also talk about circuits, right? So if you have circuits, how do you assess how good a circuit is? Well, it turns out that there are two similar quantities. One is just the size, the number of gates, and the other is what's known as the depth, which I'll sort of get into in a little bit more detail, but it's basically the number of layers of the circuit. And if you think about it, these are really quite similar between the two models. The size, the number of gates, is pretty much the same as looking at the number of processors, and the depth is pretty similar to the speed. Okay. So I'm going to take you through both of these models, and we'll see the relationship between them. But let's start with circuits. So here we have a collection of logic gates, which we'll focus on the usual stuff. But if you want to put in XOR gates and other such gates, it doesn't really change anything. And the circuits that we use nowadays are clocked, right? Which sort of means that the output is available 1 clock cycle after the input. So if you have a chain of circuits, of gates, there's a delay in getting the answer out when the input comes in. And this is why, or this is one reason that the depth determines the time till the answer is available. And so you want to keep the depth small. Now, in general, you also want to keep the number of gates small because those gates consume energy, they take area on your chip. And so this is the reason that you want to optimize both of these quantities. Now, there is an important consideration for thinking about these gates, about these circuits, which is the question of fan-in, which is the number of wires or the number of inputs to any one gate. Okay. So we can talk about a bounded fan-in, where each gate has only a constant number of inputs. Or we can talk about unbounded fan-in, which means that we can have an arbitrary number of inputs. So for example, if we want to compute the OR of n numbers, oops. Right. We can make one gate with n inputs, and that will compute the OR of n numbers, or of n bits. But suppose we wanted to do this with bounded fan-in, using only 2 inputs per gate. How could we nevertheless compute the OR of n values?
We can do 2 at a time and then put those outputs again 2 at a time. So
Exactly. And what sort of shape does that make?
A balanced binary tree.
Exactly. I can make a tree, right? Now, here I've drawn a balanced binary tree, but I mean, any binary tree would do, right? To sort of bring together all of the bits into a single result. What's the benefit of a balanced binary tree?
Shallow.
Shallow, right? So I can use depth log n to OR n bits with bounded fan-in. And the theoreticians have sort of carefully labeled and classified all of this. So we define AC of k to be the set of all functions computable with a circuit of depth log to the k of n, order log to the k of n, using a polynomial number of gates. And unbounded fan-in. Okay. And we define NC of k to be the same, but with bounded fan-in. Okay. And I will say NC of k, this stands for Nick's class. Nick's class was named by Steve Pippinger to define this complexity class that he invented. And in a lovely example of mutual back scratching, this was named by Steve Cook. There's also SC of k, which is Steve's class, which was named by Nick. And this is a class that we won't be looking at. It's for space-bounded computation. But I just wanted to flag it as an example of why it's good to be nice to the people around you, is that it might get you a complexity class named after you. So we've got the sort of bounded fan-in and unbounded fan-in complexity classes. They're parameterized by this k, the degree of the polynomial. But why is the sort of base of this exponent log n? Well, it's because a lot of things can be sort of naturally computed in log n or polylogarithmic of n depth, as we just saw with the OR computation. Right? So we did an extremely natural thing, and it gave us a log n time computation of OR with bounded fan-in. And one of the things that we know happens in the design of algorithms is composition. So when you're designing some algorithm, you may want it to do some number of recursive calls to some other algorithm, or it's not recursive, but you may want it to call some subroutines. So if you've got an algorithm that runs in log n time, and it calls subroutines that also run in log n time, then it's going to, or sorry, if you've got an algorithm that does sort of log n steps, and each of those steps is a subroutine that takes log n time, then you're going to end up with an algorithm that takes log squared n time, right? And similarly, if you start with a log squared n time algorithm and you make calls to log n time algorithms, you'll get something that's log cubed of n. So the fact that we tend to compose algorithms makes it very natural for our complexity classes to take an exponent on the sort of runtime of the canonical algorithms. So right, this is why we have a polynomial time hierarchy, is that, in sequential algorithms, linear is kind of your starting point. And then again, if you have a linear time algorithm, if you have an algorithm that takes a linear number of steps and calls a linear number of subroutines that each take a linear number of steps, now you've got a quadratic time algorithm. So polynomials emerge very naturally in sequential algorithms, and similarly, polylogarithmic runtimes emerge very naturally in parallel algorithms, because the log n is the natural sort of starting point for a lot of different, for a lot of basic algorithms in parallel. Okay. Now, I'm not going to say a lot about these classes except to point out that they are related. You can prove that the unbounded log to the kn fan-in is contained in the bounded log to the k plus 1n fan-in, which is itself contained in the unbounded log to the k plus 1n fan-in. Okay. This one, I assume, is obvious, right? if you can do something at a certain depth with bounded fan-in, then you can certainly do it with unbounded fan-in. How do we prove this one? That if you have an unbounded fan-in circuit that has depth log to the k of n, how do you turn it into a bounded fan-in circuit with depth log to the k plus 1 of n?
And if the inputs are bounded by polynomial of n, then we can use the same trick for the OR gate with the tree to add another log n.
Exactly. We replace each unbounded gate with a balanced tree of bounded gates. And this is exactly an example of the composition that I just mentioned, right? We turn each unbounded fan-in gate of depth 1 into a subroutine call, so to speak, to a bounded fan-in tree of depth log n, and that multiplies the overall depth by log n. Is that clear?
Why do we have the assumption that the number of inputs is always polynomial in n?
Well, that's stating it a little bit backwards. Essentially, n is the number of inputs. That's the definition of n.
N is the number of inputs that enters like
The whole circuit.
the whole
Right.
circuit.
So this model of a circuit is that there's a certain number of input bits, and then there's an output bit or a set of output bits.
Okay,
Right? And so
because
n is just defined to be the number of input bits. And you're allowed to build a circuit that has a number of gates, which is polynomial in that number of input bits. Okay. And this polynomial restriction, right? I mean, it makes sense, right? Gates are not free. They do take up space. It turns out that if you allow yourself an exponential number of gates, you can do really wacky things. It essentially is like, for example, you can try all the answers in parallel, right? And see which one works. So that gives just too much power. And you can sort of solve everything. So,
but I mean, the gates like in the middle, inside the circuit can have more than n inputs, right?
well, in the unbounded fan-in case, yes, right?
But it's still again bounded by
because you may very much you may. Sorry. Oh, that's okay. Sorry, I see a chat message that I can't hear you, but that's from before. So yes, in your algorithm, you might decide to replicate some of the inputs. And so you might end up with more than n wires. And so, yes, you might end up with a single gate taking many, many inputs in the unbounded fan-in case, but it's always bounded by a polynomial in this complexity class.
Yeah. Thanks.
Okay, sure. All right, and so we then, to sort of simplify our lives further, we define AC or equivalently NC to be equal to the union over all K of AC of K or NC of K, right? They're both the same. So what this is saying is problems that can be solved in log to the K of n time for some constant K. All right. So again, this is sort of like PTAS. This is like polynomial time approximation schemes. You think of K as a constant. That's not something that you make a varying parameter of your input, but it allows you to consider any large constant. It's the same as talking about polynomial time in sequential algorithms. Okay. So just as in sequential algorithms, all of the work focuses on finding polynomial time algorithms. And then once you've got one, you try and see how good a polynomial you can make. Similarly, in parallel algorithms, the goal is always to develop an NC algorithm, that is a polylogarithmic time algorithm, and then see just how good of a polylog you can achieve.
I have a question.
Yes.
So when we have n input bits, does that necessarily mean we have n wires at the start? Or could it be that we have like one wire that could sequentially give us n values? which doesn't make sense.
No, so this circuit model posits that the input is coming in on a set of wires, right? If you had one wire delivering one bit at a time, you really couldn't run a parallel algorithm because you have to wait for all of the bits to arrive.
Yeah, but when you have like mn bits and you like take m bits at a time, you could reduce the time to O m and solve it in m steps.
Right. So there are trade-offs, right? And I don't know if I'll have time to talk about this, but essentially, if you have a parallel algorithm that runs in time t with 1,000 processors, then of course you also have a parallel algorithm that runs in time 2t with 500 processors, because you can let each processor do the work of two. Right. And so there's always this kind of natural speed up, or sorry, natural what's sort of simulation that you can do. If you have only a few processors, you can simulate an algorithm with many more processors. It doesn't go the other way, right? If you are able to develop a sequential time algorithm that does a certain speed with one processor, there's no guarantee that you'll be able to go twice as fast with two processors.
Okay, thanks.
Okay, sure. All right, so now that we've got the complexity classes underneath, let's take a look at some basic problems, okay? So let's consider the problem of adding two n-bit numbers, okay? It's a little funny to think about this problem because we usually think about it as a constant time operation, right? It's something we did all the time throughout the course. But now we're really going to focus in on, the representation of these numbers in n bits and how I can produce another n-bit output or n+1 bit output that is their sum. Okay. So how did we do this in elementary school? What was our algorithm?
And we go from high precision to low precision, and we add the numbers individually, and then we have a carry at every.
Yeah, I think we actually go from low to high, right? So I take the low order bit, and I added, and I might have a carry, right? So there's no carry this time, but here there's a carry. That gives me an extra one the next time. And that's going to again generate a carry, right? And I add that. And so, right, I basically go from low to high. I add 2 bits. And I hope everybody agrees that this will take me a constant number of gates. A lot of you probably built the adder circuit, but that uses a few ands and ors, right? And you also add the possible carry. Right? And then you output the result and the carry. And those get used at the next step, right? So if I was going to draw a circuit for this, right? It's a circuit that's going to take in 2 numbers, an A and a B, and it's going to output a result and also a carry. Sorry, my pencil is strangely sensitive. And you'll take that carry, it'll take the next pair of bits, also output a result, also output carry. And you'll just sort of walk down the entire input producing these results and these carries. Yes? So what is the performance of this circuit according to the metrics that we've defined?
And it has dips and
Right. So it has depth n. And what's the other metric?
The size.
Yeah. So what's the size?
ON.
Size order n. Okay. Actually, I should probably say it's depth order n also, because each of these little adders has some depth. Okay, so as regards to size, we can't really hope to do much better because we need a circuit that's big enough to accept all of the inputs, right? But this is a pretty horrible depth, right? From the perspective, right? We saw that we only need log n depth to compute an OR. So it's kind of distressing that we need an n depth to compute an add, right? Or sorry, actually, I didn't make the right analogy. In fact, an OR can be computed in constant depth, right? If you have two n-bit strings and you want to OR them, the depth is 1. But adding them, it takes a depth of n, which is pretty horrible. So, and if we had to use this in our chips, then we would be all of our processors would be orders of magnitude slower. Fortunately, quite a long time ago, people developed this really cool idea called carry look ahead. And this achieves size order n, but depth order log n. Okay, and exponential improvement on what I showed you so far is what's called the ripple adder. It's the simplest possible adder, but the carry bits have to ripple from one side to the other, and it just takes too long. So I'm going to show you how we use carry look ahead in order to compute everything much faster. Okay, and I want to point out that the key problem is knowing the carry bits. Right? If I could somehow compute all of the carry bits and feed them directly into the appropriate gates, into the appropriate single bit adders, then I could do the whole thing in parallel, right? If I know the carry bits, I can add each input bit in parallel. Right, in constant time. So the only problem is computing the carry bits. And from the ripple adder, that appears to be a sequential process, that you only get one carry bit after you know the previous carry bit. But it turns out that we can be much cleverer than that. And so now I'm actually going to ignore the result bits, okay? Because we know that once we have the carry bits, the result bits are easy. So the real question is computing the carry bits. And what we're going to do is we're going to pre-plan for the hypothetical values of the carry bits. Okay, so in order to compute my output carry bit, I'm going to figure out sort of a case analysis around the input carry bit. And then I'm going to show how to propagate the case analyses really fast. Okay. So given a particular circuit with its two input bits, AI and BI, right? There is an unknown carry CI minus 1 from the carried from the previous gate. So the question is, what are the cases for the output carry CI? So how do I break out the cases?
You need at least 2 of the 3 bits to be 1.
Yeah, right. If at least 2 of the 3 bits are 1, then I propagate it, then CI is 1. If only, if 1 or fewer, if 0 or 1 of the bits of the input bits is 1, then I don't propagate. Breaking that out slightly differently, if AI is equal to BI and is equal to 0, then what can I say about the carry? What can I say about CI?
It must be 0.
Right, CI is equal to 0, regardless, right? And I'm going to call this a kill operation, okay? What if AI equals BI equals 1?
You definitely carry.
So CI equals 1 regardless. And I'm going to call this a generate operation. Now, finally, what if AI is not equal to BI, right? There's a 0 and a 1.
We can't be certain. We have to like look at what CI minus 1 is.
And once I look at what CI minus 1 is, what does that tell me about what CI is?
It's exactly what CI minus 1 is.
Exactly. CI is equal to CI minus 1. And I'm going to call this a propagate. Okay. So you can see that, so looking at each gate, I can see what it's going to do. I can think of it now as just something that acts on the input carry bit and produces an output carry bit. And I basically have 3 different kinds of operators, or 3 different kinds of gates. I have a kill gate, a generate gate, and a propagate gate. Right? And so I can take my circuit and I can write down the gates. And again, I can now ignore the inputs and the results and so on. And I can just say each of my gates is a kill gate or a generate gate or a propagate gate. Right? I further know that the first gate doesn't actually have an input carry bit, right? So I'm going to start with a 0 going into this thing. Yes? And so now I need to understand what happens to that 0 as it propagates through each of these gates, or through each of these operators, right? So the carry here, right? This is the result of applying generate to a propagate to a generate. Whoa, sorry, I don't know why my computer does that sometimes. So if the result here is going to be the result of applying generate to propagate to generate to 0, right? And that's going to be the carry that's output by the third gate. Or to put it another way, I can think of composing the operators, right? I'm composing generate with propagate with generate, and I'm applying that to 0. And so in order to understand that composition, I'm going to design my multiplication table for these 3 operators. So in particular, suppose that the gate I minus 1 may be a kill, a propagate, or a generate. Gate I could also be a kill, a propagate, or a generate, okay? Now suppose that I compose those 2 things, right? Suppose that I have 2 gates and the first one kills and then the one after it also kills. What is the combined effect of those 2 gates?
kill.
It's a kill, right? The output carry from, right, whatever the input is to that sequence of 2 gates, the output is going to be a 0, right? Now I claim that in fact, that is true just because xi is a kill gate. It doesn't actually matter what xi minus 1 is. In all cases, xi is going to override and kill the carry bit if xi is itself a kill gate. Similarly, if xi is a generate gate, it doesn't matter what xi minus 1 is. It's going to override, right? And generate a carry. What about the middle row?
It matches xi minus 1.
It matches xi minus 1. So we have kill, propagate, and generate. Okay? So now we have this multiplication table, and you can check that this is an associative operation. It doesn't matter how you set up the parentheses. So we can compute the result of chaining together many of these gates by combining them in pairs and working our way up. Okay. Does this make sense? Now, here's another thing to notice. The first gate is a kill gate, right? And more importantly, it's not a propagate. Okay, so x0 is not a p, right? Now, if x0 is not a p, it means the product of x0 by x1 also won't be a p, right? Because the only way you can get a p in that product is if x0 is equal to a p, right? And similarly, because x1 is not going to be a propagate, it means that x2 can't be it means that the product of x0 times x1 times x2 also cannot be a propagate, right? And so by induction, okay, xi times xi minus 1 times xi minus 2 all the way down to 0 is never a p. Okay. It's always k or g. Right? And that's great, because if every one of these products is a K or a G, that tells us the value of CI, of the output carry bit, right? The product of the output carry is 1 if xi producted all the way down to x0 is equal to k, and it's 0 if the product is equal to a G. Okay. So this is a little bit abstract. We're basically doing abstract algebra here with this weird set of operators, K, G, and P. So I want to pause and make sure that what I've said makes sense to everybody. No questions about it?
Wait, should it be 1 if xi?
Oh, sorry, I got it backwards. Thank you. Let's turn it around. Good. This tells me at least one person is following. Do other people have questions or corrections?
While we're still in the making sure we're following, you did some sketchy binary addition earlier.
Sketchy binary addition. Can you elaborate?
Scroll up.
Oh, did I actually add my bits wrong? You're right. This should be a 0.
Yeah.
Are we better now? Yeah, I think
We're
it's
closer. We're a little closer.
okay. Oh, thank you. Let's
010.
yeah, I shouldn't be allowed to use actual numbers. I'm a graph theorist, not a numerical analyst. Okay, so everybody's on board with this, and so the summary is that we're given these xi's. which are each a P, G, or K. And for CI, we need to compute xi composed with xi minus 1, composed with xi minus 2, all the way down to x0. Everybody buy that? Okay, so for historical reasons, or sorry, it's very sensible, this is known as prefix sum, okay? Because, or I mean, the way I've written it, you might want to call it suffix sum instead, but basically I need, you know, if I write these out, I need this product, I need this product, I need this product, I need this product, and I need this product, right? So I need the products of all the suffixes of the operators, of the chain of operators, okay? Now, if I was going to compute this sequentially, right? I have n different outputs I need to produce, but how long would it take me to produce these n outputs sequentially?
N time.
How would you do it?
I mean, if you're, so by sequentially, you mean you're going to take the, so you're going to do x0 times x1, then you're going to multiply by x2, and then x3, and then just go down
Exactly.
the chain.
I basically create this recurrence, or this chain, where I set output I to be input I times output I minus 1. Yes? And I guess I would start with y0 equal x0. Okay, so I can do n computations, I do n outputs, order n time. And if you think about it, this is exactly what the ripple adder does. Right? It generates each carry from the previous carry. But what we want is a more efficient parallel prefix algorithm. So how could we compute all of these outputs faster than the sequential time? And let me start with a more simple question. How can we quickly compute the product of all of them? Let's forget about the prefixes.
I mean, you use associative property here, right? So you can group your parentheses however you want. So you can just do the tree.
Exactly. I can use the same trick of making a binary tree over the inputs and leveraging the associative property, I can compute the product of everything at the root. Right, so I get x1 times x0 over here, and x3 times x2 over here. And up here would be x3 times x2 times x1 times x0. And up here we'd have the product of all of them. And this works for any associative operator, right? So that gives me the value, the product of all of them. But I want each prefix. Okay, so staring at this tree, can we maybe get some insight into how I might compute all the prefixes? I mean, actually, there's an easy way. Right now that I see how to compute the product of all of them, what's a naive method that will just give me all of the products?
Make a bunch of trees.
Yeah, if I wanted all n products, well, I could just use n trees, right? And so this is already fantastic, right? This is going to be order log n depth, because each tree is log n depth, right? It is, however, going to use n squared gates. Okay, so we have already successfully shown, I mean, I've left out some details here because I figure, you know, we're probably far along enough in the class now that I can leave out some details. I've shown you how to compute the carry bits, and so now you can go back and feed those into the adder in order to perform the addition. So now that we've solved this critical problem of computing the carries in NC, that means that addition can be solved in NC, right? However, this n squared gates is wasteful, all right? What we would like to do is get back to the sort of linear circuit sizes that we had for simpler problems. So any thoughts on how we can avoid using n different trees?
Basically, we can use log n of the outputs of one tree to compute
Great.
any.
So, sorry. Okay, so you even went farther than I was saying. Yes, so we can in fact use combinations of the outputs of subtrees to get everything else. Right now, the simplest observation is some of the prefixes we've already computed in this tree, right? Which prefixes have we already computed?
Powers of two.
Yeah, I mean, we've computed the ones that I actually flagged, right? We computed the x0 prefix, we computed the x1, x0 prefix, we computed the x3, x2, x1, x0 prefix, right? So this tree all by itself already gave us log n prefixes, right? But we can go farther, right? We can observe that we can assemble any prefix from log n subtrees of this one tree, right? So for example, how would I compute the product of x6, which is the x6 prefix, right? x6 times x5 times x4 and so on. How would I build this from existing answers?
So I guess you would take the x3, x2, x1, x0 answer, then the x4, x5, and then the x6.
Exactly. So you see, I can make the answer out of 3 trees. Okay. And you could do it that way. You could just sort of make copies of the outputs of the different trees and mash them together. But this would actually generate high fan-outs, and you would have to actually increase the depth if you wanted to get it back to bounded fan-out. And high fan-out is as bad as high fan-in. Practically speaking, it's very difficult to make a gate with high fan-in or high fan-out because of the power requirements. If you want to drive a lot of different gates. So instead, what we're going to do is feed the subtree values up and then back down. Okay, so the point is that, here I've computed x1 times x0. I am going to propagate that up to the parent node, because I know that certain siblings are going to need x1 times x0. I'm actually going to send that back down to my left sibling. Okay, and this left sibling can now convey x1 times x0 down to its child that needs it for its own prefix computation. Okay. And so I'm not going to fill in the details. I'll leave that up to you, right? But essentially, you pass up the product of all your children once you get it. And you also pass it down the product of my left children, of my right subtree, to the left subtree, or to my left child for use in the left subtree where needed. And if you do this carefully, you end up with what we need. Log n depth, order log n depth, and order n gates to do the prefix sum.
I mean, we already had the order of log n depth with just the naive approach, right?
That's correct.
Because
what I've shown you here is a way to save on the number of gates.
But I mean, like, what is this sending down buying for us?
It's reducing the number of gates that we need. Okay.
It's reducing its order, or you mean the constant?
This will have a constant factor higher depth. Okay. So yeah, let me draw the circuit the way that you would actually be thinking about it as a circuit, right? So you've got this gate, and it takes its two children and applies the proper operator to combine them. It combines these two children, right? And it passes the value of that as an input to the parent gate that's going to combine with the left child. But what you're going to do is you're also going to fan it out to another gate that's here, whose job is to pass it down to the left sibling. Okay, or actually, probably a cleaner way to write it is to say that this value is also going to be propagated to my left sibling. Okay, and I have one gate here in the left sibling that is computing the product of the two children and sending it up to the parent. Yes, but this gate is also, there's going to be another one that is responsible for combining the whole right subtree with the results of the right subtree over here in order to get another one of the prefixes.
Right.
Okay.
So I mean,
So
I guess this
it's more intuitive to think about these nodes as little processors that send information and receive information, but each of them, if you're actually building a circuit, you would make a number of gates, one to do each of the things that's needed at that particular node of the tree.
right, but I guess like my point was, so basically without this operation, we would still get O log n depth and O of n gates. But I feel like this particular way of doing it gives us like exactly log n depth without any constant.
I think you may need 2 log n, but as a theoretical computer scientist, I am opposed on principle to thinking about the constant factors.
So, I mean, do you agree that like the previous approach also would give the same depth time?
Well, so again, we got log n depth with n squared gates.
No, not that one, like just this.
This one of assembling subtrees will give us log n depth, but because each prefix is going to be used several times, it creates a fan out problem.
Okay, I see.
Right? So each of the outputs, each of the subtrees is going to be wanted by log n different prefixes.
Yes.
Or I think that's right. And so you would need to do a log n fan out if you wanted to do that in one step. And instead you would need to use our binary tree trick, which would multiply the depth by log n.
I see.
Okay.
Right.
So yeah, so you need this for the optimum structure. Okay. All right. So there's a whole rich literature in what is known as circuit complexity. Which really studies, what kinds of functions can be computed at various depths. And because this is actually quite a weak computational model, these low depth circuits, it's one of the few places where we actually have lower bounds that are unconditional, right? So we have things like computing parity using AND and OR gates. requires, I think, log n depth, right? There's lots of work on what's called AC0, right? So unbounded fan-in constant depth circuits and what they can compute, okay? But as soon as you go beyond the very lowest part of the hierarchy, it becomes a lot more intuitive to think instead about processors. And so we're now going to switch to what's called the PRAM, the Parallel Random Access Machine. And that's what I'll talk about for the rest of today and on Friday, to give you a sense of how people design parallel algorithms as opposed to designing parallel circuits. But it's that time. Let's take a 2-minute break first, and then we will resume. Everybody should get up and dance around a little bit to get the blood flowing again. All right, it looks like my pad went to sleep again. While I wake it up, let me talk a bit about logistics. Did you lose my screen? That's so
Yes.
weird. It still thinks I'm sharing. Logistics. As I mentioned, I messed up on the class scheduling and was planning to hand out a final problem set today that was due before Thanksgiving break, which I assumed was next Wednesday. Since break is starting on Monday, I'm going to hand out half a problem set. So it will have only 2 or 3 problems. So technically you can finish it before you go on break. In order to not force you into squeezing it into the 2 days, if you have other P sets due in the next 2 days, I'm going to make it due the week after Thanksgiving, in the Wednesday after Thanksgiving. And again, it's going to be short. So if you just want to start it on Sunday when you get back, that will work fine as well. One exception, one required problem on this P set is turning in a project proposal. And that is something that I would like to have in before Thanksgiving, before break begins, so that I can give you feedback and you have time, if you need to adjust your planned project. All right, so hopefully you've already begun, planning out your project and finding collaborators and such. There was a question last time about whether we were going to constrain who your collaborators could be, and the answer is no. You can collaborate as you wish. And we want you to collaborate. The final project should be a collaboration. If you want to do it alone, we need an explanation for why. Now, I assume that some of you have been thinking about projects and the logistics of the final project. Are there any questions about it? None. Everybody's happy? Everybody understands the plan? All right. Friday will be the last lecture. Friday will be the last time I lecture, and we will not have class in the week following. The one remaining class that we will have, yes, if you can, as long as you get me the project assignments before you head home, whenever that is. Sorry, the project proposals before you head home. So Sunday is fine, but get them in so that I have time to give you feedback. Yeah, let me say a couple of things about the project. And most of this is in the handout, but some stuff I want to emphasize. One is that I will be getting on the order of 30 or 40 projects. And so that means that I'll probably have about an hour to spend reading each of them, optimistically. And you should write a project for somebody who's reading it for an hour, not somebody who's reading it for a day. Okay, it should not require more time than that to understand the ideas. And that is the point of this project, is to convey the ideas, right? You don't need to formally prove everything. It's much more important for me to be convinced that it's true than it is for me to check every line of a proof, because I'm certainly not going to have time to do that. And you're reporting what somebody else did, and their paper was already reviewed, and so we can assume that the proofs are correct. So I'm really looking for the insights and not for the formal methods. I'm also terrible at math and algebra, so I wouldn't be able to follow too much of the math anyway. You should write this paper not specifically for me, but for a random other person in the class. It needs to be understandable by anybody who has taken advanced algorithms. Okay, and if you give me something that I happen to understand, but that I think that people in the class would not understand, I'm going to deduct for that. Okay, the measuring stick is the typical student from this class. So you're welcome to rely on anything that was taught here, but you can't rely on any other knowledge of theoretical computer science beyond what was in this class. Okay, and in order to provide a check on that, the lecture before the last lecture, which will be a Monday, will be a peer editing session. You will be coming to class with a copy, not a physical copy, but with a generated copy of your project. And we will spend an hour in class reading each other's projects and commenting on them. And this will be the last assignment before the final project. You will be required to turn in comments on somebody else's project proposal. You'll be emailing them to the author and also to me. And then the recipients will have 2 days at least until the formal deadline of the project to take those comments and use them to revise the project, to revise their submission. And I have found, since I introduced this, that it dramatically improves the quality of the submissions to have somebody else from the class look at them. And so, you know, there are always a few students who show up on Monday and say, well, we don't have our project written yet. You know, that will be your loss, because you will get a higher grade if some other students actually look at your projects.
Which
Okay.
Monday is this again?
When is the last Wednesday of class? Is that like December 14, hang on a sec.
December 9th.
I don't have the calendar in front of me.
December 9th, I think. Yeah.
Okay, so yes, so it will be, that's November, hang on. So the last day of class is December 9th, so this will be on December 7th,
Okay.
okay? All right, on to PRAMs. So the PRAM model goes back to a collection of processors. So the idea here is that we have processors running synchronously. So that means in each time step, each processor does one operation, okay? And they can perform local computations as those operations, typical processor. They also can read or write a shared memory, which is a RAM, just like our standard model of computation. So we take our standard model, but we allow there to be multiple processors, and they all work in lockstep, and they all can read or write from the same memory locations. Okay. Now, as soon as you allow this idea of multiple processors reading or writing from a shared memory location, you have to worry about conflict resolution. Right? So what happens if two processors read or write the same memory location? Right. So for reads, it seems easy, right? They should all get the value. But if you look at the way parallel processors actually have to be implemented, right? In order for two processors to get the value has to be delivered to all the processors that want it. And so you have in practice the same problem as you have with fan-out, that you know, there may be sort of, you know, messaging chips or something for delivering information from the memory to the processor. And even though the system is parallel, that memory chip that memory chip might only be able to deliver the data to one processor at a time. This can cause a slowdown if multiple processors try and read at the same time. And so in order to address this, theoreticians describe these separate models of what's called an exclusive read model, which says that only one processor at a time can read a memory location. In one step. Okay, if another wants to read, it's going to have to wait. There's also concurrent read, which says that many can simultaneously read from the memory location. And if you think about it from the perspective of circuits, exclusive read is a lot like bounded fan-in. And concurrent read is a lot like unbounded fan-in or fan-out. Make sense? There's a similar issue with writes, right? You may have exclusive write, right? Which says that only one processor can do it. Or you may allow concurrent writes. However, if you allow concurrent writes, there's now another question that you need to answer, right? What gets tricky if you allow concurrent writes?
Who is right?
Yeah, now there may be competing values. Right? And so you have to decide how to resolve the competing values. And there's several ways that people do this. Some people say, some models say that you'll get an arbitrary result. Some say that you'll get a random result. Some say that you'll get the maximum or the minimum result. And some say you'll get garbage, that it's allowed, but you can't control, but the result will be jumbled. Okay.
Excuse me,
So
can I ask a question?
yes,
The system is totally synchronous with some
totally
clock?
synchronous. So in each step, every processor can either read or write or do one operation like an add or an if.
Okay, I see.
Okay. All right. So now that we've got these notions of different kinds of conflict resolution for reading and writing, you can make acronyms for these, right? CRCW, concurrent read write. That's a nice model. People like CREW because, again, concurrent reads, it kind of is clear what should happen. But as long as you enforce exclusive rights, you don't have to decide on a resolution strategy for mixed values. And people also talk about exclusive read, exclusive write. Okay. Finally, to talk about complexity classes, we define CRCW of K to be equal to problems solvable in log to the K of n time using a polynomial in n number of processors in the CRCW model, right? And similarly, you can have, EREW of K and CREW of K, so on and so forth. NC of K, Nick's class, is basically the same thing. It's kind of sloppy about CRCW versus EREW. Okay. Now, exactly as with circuits, right? In circuits, we talked about how to simulate unbounded fan-in with bounded fan-in. Similarly, with parallel algorithms, you can show that CRCW of K is contained in EREW of K plus 1. That is, if you want to design a concurrent parallel algorithm with log to the K of n runtime, you can turn it into an exclusive read-write algorithm with log to the K plus 1 of n running time. How do we do that? Same trick. We use a binary fan-in tree. So essentially, we can imagine that our RAM is over here. And if we want to prepare that RAM to accept reads from possibly n different processors, we just use some more memory to define a binary tree over that one memory location. And we use our n processors to march n values down the binary tree. Basically, in a single step, the two nodes that might be trying to write will talk to each other using the parent node, and they'll agree on which of them gets to go forward, right? So it's like a little tournament to get to see who gets to actually write into the memory location. Okay. So I won't give more details unless somebody wants to ask.
This actually can do more than the CRCW model, right? Because in CRC, in like concurrent, we might end up having something random or nonsense.
That's correct. So the point is that you can simulate any one of the CRCW models using this fan-in trick. And because you're implementing it in an EREW model, the EREW model doesn't need any conflict resolution rules. Right? So you don't require any particular architecture, and you can simulate any architecture that you want with a log n time slowdown.
Thanks.
Okay, good. And so again, just as with, I already mentioned NC. NC is now the union of all of the different constant polylog. It's the union of all the polylog time algorithms. Okay. Now I said before that it's also the union. Sorry, it's the union of all the CRCW algorithms. It's also the union of all the circuits, right? But if you think about it, this is not hard, right? Any circuit of depth d can be simulated by a PRAM. Depth d and G gates can be simulated by a PRAM with G processors in time d, right? You just put a processor at each gate and you have it do the work of the gate, right? And conversely, any PRAM algorithm with n processors in time t can be built into a circuit with basically n polylog of n gates and depth t polylog of n. Right? Again, essentially, you make a few gates to handle each time step of each processor. And you feed the output, and also some gates to handle the different memory locations. And you essentially move the memory into the circuit as gates, and you feed the output of step t into the gates that represent the memory at step t, and then those become the input gates for the processors that are going to, for the gates that are going to simulate the processors at step t+1. Okay? So there's no ambiguity in the definition of this complexity class because both of these models define exactly the same power of computation, circuits and PRAMs. Okay? So that's an introduction to the PRAM algorithms. Let me use the last few minutes to quickly point out that there are actual meaningful differences for EREW versus CRCW. So for example, suppose that I want to compute the OR of n bits. How long does that take me in these two models?
So in CRCW, probably log n, but in EREW, it's ON.
I would say both of those measures are pessimistic. Right? If it takes you order n time to do an OR of n bits in EREW, then parallel algorithms are doomed, right? We don't want such a simple thing to take linear time. There'd be no point in parallelism.
We can do login in EREW, and if we have, say, the min rule for dealing with race condition, and we can do 1 in CRCW, be like, let's have everyone race, and we'll select the min one.
All right, so that works for a particular model of CRCW. Actually, let's finish EREW first. So how do we do this in log n time?
We do like kind of the fanning tree approach where
we do an OR tree, right? Basically, we put a processor on each of the inputs, and two processors look at their inputs and they can take turns, right? If processor 1 sees a 1, then it can say, I saw a 1 on the first step. If processor 2 sees a 1, right, it can look and see if processor 1 saw a 1. If processor 1 saw a 1, then processor 2 won't do anything because we already know the answer. If processor 1 saw a 0, then processor 2 can say, well, I saw a 1. Okay, and so after 2 steps, we know the value of x1 or x2. And we'll also know the value of x3 or x4 and x5 or x6 and so on. So we've just cut the number of bits in half. We repeat that process to OR together all of the bits in log n time. Now CRCW. Okay, so one idea was, if we have the proper resolution rule, right, we can simply write down, every processor can just write the value that it sees into the memory location, and the resolution rule will do the OR. So that's true for certain resolution rules, but if, for example, we have the, the random or the garbage resolution rule, that won't work. So can we develop a more robust method for doing an OR in CRCW that will work regardless of the model? Actually, let me back up from that. Can we do something that will work as long as, so sort of the minimum you could hope for in a CRCW is that if all the processors are writing the same value, then that's the value you'll see, right? So let's posit, right? That's true of random, that's true of arbitrary, it's true of max, right? The only one that violates it is the garbage one. But as long as you get a value that you wrote, how can we compute OR quickly with CRCW?
If it's not 0, it's a 1.
Correct. But how do we turn that into an algorithm?
Have everyone write if we get some, then,
Yeah, so this is actually where it's easier to think about processors than circuits, because you can have conditioning, right? You can have conditional steps. So all I'm going to say is each processor checks its value. Or sorry, let me back up. First, we're going to init the output to 0. Then we'll have each processor check its value. And if it sees a 1, it will write it to the output. So only processors that have a 1 will write. So only 1s will be written. So if any processor has a 1, then a 1 will be written. If no processor has a 1, then nothing will be written and the output will still be 0. So all we're using is the ability to kind of condition what processors do based on their input. Okay, and so this is a case where CRCW is log n faster, a log n factor faster than EREW, right? We've already seen that that's the worst case because we can simulate with the log n factor slowdown. Okay, now that was pretty obvious. Let me set you as a puzzle for Friday. This is the first thing I'll cover on Friday, and it's in the notes if you want to check the answer, but it's fun to think about. How fast can you compute the maximum of n values? Okay, so in EREW, this is pretty obviously going to be log n again, and you can do it that is, it's at least log n, and it's easy to do in log n. But what can you do with CRCW? It turns out there are some fun tricks you can play with CRCW to get good answers to this question. And that's where I'll start on Friday. And then I'll take you through a tour of some of the other basic PRAM algorithms to get some sense of this computational model. Any final questions?
So in the method for the OR of n bits for CRCW, what if processors see 1 and they want to write it to the memory location? If under a model, what's going to be written is going to be garbage, it's not necessarily
right. So that's what I said. This requires, this works for all the models except the garbage model.
Oh, okay.
Right. It works for the max model, for arbitrary, for random, right? Because all that's required is that the value that's stored be one of the values that's written, because the only value that we're writing is a 1.
And I think a little ways back, you said something like CRCW, all problems solved by CRCW of K are solvable by EREW of K, but that seems a little bit
It's of K plus 1,
of K plus 1? Oh, okay, now that makes sense.
right? That's the point. There's a log n factor slowdown because you have to do these fan outs. You have to simulate these fan outs.
Okay, that makes sense. Thanks.
I have a
Okay.
question about the correspondence between the circuit classes and the processor classes.
Yes.
Can you elaborate on that a bit more rigorously?
Yes. I mean, everybody's free to go, right? But essentially, the basic operations of a processor, like comparing two numbers or adding two numbers and so on, they all correspond to log depth circuits. So a single processor step can always be implemented with a log depth circuit.
Okay.
So if you have a whole series of processor steps, right, you need to chain together those log depth circuits, and the overall height of the circuit is going to be the log n times the number of processor steps. Okay.
Log n times the I mean, the depths are okay. I see. You're right.
Okay. So that means that if you've got a PRAM algorithm that runs at a certain time, right, then you need to chain together the operations that each processor performs at each time step. And so the depth is going to be log n times the PRAM time.
Right. So we have an increase of 1 in K. When we
Yes,
go.
that's right. But again, remember the main complexity classes like NC says it just needs to be some constant degree polynomial in log n. So multiplying by log n doesn't take you out. It keeps you in that complexity class.
So it defined the union of the concurrent model and the other model as NC.
The union of the concurrent model is equivalent to the union of the exclusive model, and that's equivalent to the union of the circuit models at all polylogarithmic for all values of K.
And is there a way to, so basically I'm thinking about when you want to transform the model that has unlimited fan-in to the processor model.
Yeah, well, again, we have this whole collection of transformations, and each of them causes a log n each of them may have a log n multiplicative effect. But if we only do a constant number of those transformations, then again, it only changes the degree of the polylog. It doesn't take you out of that.
But if you want to transform it to the concurrent model, can we reduce one log factor?
Oh yes, so the complexity people don't care what the K is, right? They just want to know that it's a constant.
Yes, but just out of curiosity. Like.
Yeah, no, in practice, there are very careful things that you can do to keep those polylogs from blowing up. But I'm not sure what the optimal things are. It depends a lot on your exact model, right? What operations of your processor do you need to simulate, right? If your processor only does ands and ors, then you may not need an extra log factor. If your processor is doing addition, then you might need it after all, right? So that gets very much into the details of exactly what you're trying to transform.
Right, but we're sure that like if you want to go from 1K in one model to the other, we at most pay log n.
Yes, we know that it's at most log n, and we know that it's at least log n, right? As I just showed you with the or sorry, I didn't prove it to you, but you can give a lower bound of log n on the time it takes to compute or using exclusive read, exclusive write.
What, like, I mean, we also have to pay for so once you should pay for the like the processor's operations. You should pay 1 log for that. You also should pay for having unlimited fan in
Yes.
another log.
Yeah, and again, depending on your exact model, it might be possible to pipeline these things, so to speak, to kind of overlay so that you only
Drop
pay
1
once.
log, you mean?
Yeah, but again, nobody really wrestles. People don't. You can't think about those details in general. You need to look at exactly what your model is that you're trying to transform. Like
Right.
what operations are you trying to support and so forth.
I see.
Okay.
Got it. Thanks.
Sure. All right. Goodbye, folks. We're